This is section 13.3 on arc length and curvature. All right, so we're on page 861, it looks like. So arc length, similar idea to what happened in 2 dimensions. In 3 space, you might recall from Calc 2, to find the length of a curve defined parametrically, we have the integral from a to b of the square root of dx dt squared plus dy dt squared. So it's no big deal to guess that for 3 space, you just add the dz dt squared, and that gives you the arc length in 3 space. So if you want to find the arc length along something like this, right? So on page 862, and this is probably what you want to put in your formula sheet. Arc length is the integral from a to b of, you can have either this f prime of t squared plus g prime of t squared plus h prime of t squared, square root of the whole thing, dt, or square root of dx dt squared plus dy dt squared plus dz dt squared dt. Okay, you could also put it more compactly as the integral from a to b of magnitude of r prime of t dt. All right, so that's how you find arc length. Sometimes we have occasion to do something called an arc length function, and I'll show you when that happens. Okay, but on page 863, after number 7, ds dt is equal to magnitude of r prime t. It is often useful to parameterize a curve with respect to arc length, and I'll show you how to do that eventually, but they give you an example there. Okay, where instead of having a function of t, you have a function of s. And so you just need a relation between the two. In this particular example, it looks like ds dt is radical 2, which means s is equal to radical 2 t. So they just make the substitution. So in the final answer, right over here, instead of putting t, they replace it with s over radical 2, s over radical 2, s over radical 2. Okay, curvature is a measure of how fast the curve is moving. So if you look at figure 4, as you go along the curve, well, some parts look more curved, quote unquote, than others. So right here, it looks like there's a sharp curve, so it have higher curvature. On the other hand, if you're like a straight line, then there'd be no curvature at all. Okay, and that has, of course, applications for roller coasters, especially, right? You know, some roller coasters, you have parts of the curve which are very curved, so to speak, and others that are not curved whatsoever. All right, so we have this formula, we've seen that before, that unit tangent vector, t of t is r prime over its magnitude. Okay, now definitions of curvature and formulas for curvature, page 864. This is correct, although it's useless as far as working problems out. It's the rate of change of the tangent vector as we move along the curve. Okay, so the letter we use is kappa. It kind of looks like a K, a funny looking K. This is the Greek K. Okay, so the rate of change of the unit tangent vector as we move along the curve. How does the tangent vector change, the unit tangent vector change? All right, this might be useful. So put this on your cheat sheet. Kappa, curvature, is magnitude of t prime over magnitude of r prime. Okay, and a side note, they go through the derivation here. You can look at it or not. But the curvature of a circle of radius a is 1 over a. That kind of makes sense, which means the smaller the a, the higher the curvature. So if you have a real tiny circle, imagine draw a circle like that. It's highly curved. We're going around quite a bit. But if the radius is super big, like the radius of the Earth, well, we know, for small regions, we don't think of the Earth as even being curved. It takes a long time, or many, many miles, until you actually start to see the curvature of the Earth. But for most short distances around the Bay Area, we don't think of the Earth as being curved. We pretend that it's practically flat, right? So if you go a real tight circle, draw a circle real tight, it's highly curved, okay? So a real circle like so. Well, it's quite curved. But if your circle gets really, really big, okay, I'm just drawing a smart, this is even not exaggerated, okay? If I were to keep going, then you say, oh, it's barely curved at all. It's not even curved, right? Okay. All right, another useful formula for kappa is magnitude of r prime cross r double prime over magnitude of r prime cubed. Okay, so we'll be using that from time to time. The text goes over the proof. You can look at it or not. That's up to you. All right, and then if you have a plane curve, you're back in y is a function of x. Okay, equation 11, the special plane curve y is a function of x. All this calculation comes out to be this. Kappa is magnitude of f double prime over 1 plus f prime of x squared raised to the 3/2 power. Okay, and I just mentioned off to the side, as side note, if you have a linear function in 2D, linear function is mx plus b. First derivative is m, second derivative is 0, which means the numerator is 0. Okay, and that makes sense because if you have a line, well, a line is not curved, so if you have any line, then kappa is automatically 0, which makes sense. It's not curved at all. Okay, all right. All right, special vectors, normal and binormal vectors. Put these on your formula sheet. Okay, unit normal is t prime over magnitude of t prime, unit normal. And then you have a binormal vector, and they kind of give you a picture here. But the binormal vector, capital B, is t cross n, cross product. Okay, and this is more applied to physics. You physics people may have heard of this, something called the TNB frame for any particle in motion. This is quite useful for flying objects, like flying spacecraft or planes. Okay, at any point you have something called the TNB frame. So tangent, normal, and binormal, tangent, normal, and binormal, they're all perpendicular to each other, or orthogonal to each other. So unit tangent, we know the tangent vector. Okay, unit normal and unit binormal, and they're all perpendicular to each other. How do we get them? Unit normal is that, and binormal is here. In fact, there's a nice little summary of all these formulas on the bottom of 867. You're welcome to put these on your cheat sheet. Okay, unit tangent, unit normal, binormal, okay, and you have formulas for kappa. That first one is just a definition, magnitude of dt, ds, but that's useless pretty much as if you're trying to calculate them. Use the second one or third one, magnitude of t prime over magnitude of r prime, or the third one, magnitude of r prime cross r double prime divided by r prime cubed. All right. Okay, so 13.3, 868. And for the benefit of those of you who don't have the text and aren't getting it. Again, I feel justified in doing it quickly because you can always pause, rewind, fast forward as much as you want. And find curvatures, find curvature, find curvature. And here's some more. Yeah, I don't think I gave you any problems there. Oh yeah, find a curvature. Find T and B. Okay, I don't think we had to do any problems here. So that is that. Okay, number one, arc length. There's R of T. So the arc length integral from -5 to 5 of dx dt squared plus dy dt squared plus dz dt squared dt. So derivative of t is 1 squared. Derivative of 3 cosine t is -3 sine t squared. dz dt is 3 cosine t squared. 1 plus 9 sine squared t plus 9 cosine squared t. That comes out to be 9. Okay, so that's radical 10. Okay, integral from -5 to 5 just turns out to be the length of the interval. Okay, so 10 radical 10. Side note, okay, if you ever integrate just dx, it's the length of the interval. Okay, so integral of 1 dx, it's x from a to b, so that's just b minus a, which is the length of the interval. Okay, number 3, r of t is radical 2t, e to the t, e to the negative t. So dx dt squared is radical 2 squared. dy dt is e to the t squared. dz dt is negative e to the negative t squared. Okay, so that comes out to be e to the 2t plus 2 plus e to the negative 2t, which very conveniently factors into e to the t plus e to the negative t squared. So if you square a square root, just take off the square and the square root. So you're integrating e to the t plus e to the negative t, which comes out to be e to the t minus e to the negative t. You plug in 0, you get 1 minus 1, which is 0. Plug in 1, you have e to the 1 minus e to the negative 1, or e to the t minus e to the negative, e to the 1 minus e to the negative 1. Okay, 13 is one of those problems where they ask you to change the parameterization, and I'll show you what's going on there. 13, find the arc length function for the curve measured from the point P to the direction of increasing t, and then reparameterize the curve with respect to arc length, starting from P, and find a point 4 units along the curve in the direction of increasing t for P. So you're not necessarily interested in the time, but you want to know where am I after so much arc length, as it were. So here's what you do. So first I find ds dt, which is the magnitude of r prime of t. So derivative of this is -1, square it. Derivative of this is 4, square it. Derivative of this is 3, square it. I get radical 26. In other words, ds dt is radical 26. So ds dt, that means ds is radical 26 dt, or integrating s is radical 26 t. All right, so s of t is radical 26 t. Oh, I'm sorry, it actually should be t minus 1 because they told us to plug in t is 1. So this should be t minus 1 right over here. So s of t is, trying to get this thing to focus for me, radical 26 t minus 1. Do a little bit of simple algebra. T is s over radical 26 plus 1. Okay, so my r function, r is t of s, is 4 minus s over radical 26, 4s over radical 26 plus 1, 3s over radical 26 plus 3. So all I did was take this t and change it to that, change this t and change it to that, change this t and change it to that, and that's what you end up with. Okay, then part B, S is 4 units. I want R of T of 4. Okay, so you plug in 4 for T right here. So that gives me 4 minus 4 over radical 26, and plug in 4, 16 over radical 26 plus 1, plug in 4, 12 over radical 26 plus 3. Okay, 15, they give me this, start at 0, 0, 3, which tells me that t is 0. How do I get that? Probably the easiest one is to look over here. All right, so r prime is derivative is 3 cosine t, 4, -3 sine t. Magnitude, square root of this thing squared, plus this thing squared, plus this thing squared. 9 cosine squared plus 9 sine squared is 9. 9 plus 16 is 25, square root is 5. Okay, which means ds dt is 5. Okay, or ds equals 5 dt, which means s is 5t. Okay, so integral, so ds is 5 dt, integrate s is 5t. So t is s over 5. All right, so 3 sine of t, which is now s over 5, 4 t over 5 is s over 5, and 3 cosine t over 5 is 3 cosine s over 5. Okay. Now they just tell me to plug in 5. So I plug in 5, 3 sine of 1, 4, 3 cosine of 1. All right, 17, they give me r of t. So t is r prime divided by its magnitude. So derivative of this is 1, negative 3 sine t, 3 cosine t, divided by its magnitude. 1 plus this thing squared is 9 sine squared t. This thing squared is 9 cosine squared t. Similar game, that's 1 plus 9. So 1 negative 3 sine t, 3 cosine t over radical 10. Then unit normal is t prime over norm of t prime. So 1 over radical 10 over this derivative, 0, negative 3 cosine t, negative 3 sine t, okay, over its magnitude, 1 over radical 10, which will just cancel out. Okay, 0 plus 9 cosine squared plus 9 sine squared. Okay, that comes out to be 3. So if I just divide by 3, I lose that, and I lose that, I lose the 1 over radical 10s. So it's simply 0, negative cosine t, negative sine of t. Okay, kappa, magnitude of t prime over magnitude of r prime. So magnitude of t prime is 1 over radical 10 times 0, negative 3 cosine t, negative 3 sine t. That's 1 over radical 10. Remember, this was 3, right? It was 9 cosine squared plus 9 sine squared, which is 9, whose square root is 3. So 3 over radical 10. Magnitude of r prime was 1, negative 3 sine t, 3 cosine t is radical 1 plus 9 cosine squared plus 9 sine squared, which is 9 radical 10. So therefore, kappa is this thing, 3 over radical 10, divided by this thing, which is radical 10. Final answer is 3/10. Okay, 21. This was r. Okay, so r prime, 0, 3t squared, 2t. R double prime, 0, 6t2. Take the cross product, ijk, 0, 3t squared, 2t, 0, 6t2. So the I component is that minus that, 6t squared minus 12t squared. J component is nothing minus nothing. K component is nothing minus nothing. So just negative 6t squared, whose magnitude is 6t squared. Okay, magnitude of r prime is square root of 0 squared plus 3t squared squared plus 2t squared. Okay, so kappa is magnitude of the cross product, 6t squared over this thing to the 3/2 power by formula, 9t to the 4th plus 4t squared raised to the 3/2 power. Okay, using this formula here for kappa. Okay. All right, and let's see, 25. It's r of t, t squared t cubed. At 1, 1, 1, that means t is 1. R prime, 1, 2t, 3t squared. Double prime, 0, 2, 6t. Take the cross product, ijk, components of r prime, components of r prime. Okay, so the I component is, let's see, 12t squared minus 6t squared is 6t squared. J component is the opposite of 6t minus nothing. K component is 2 minus nothing. So 6t squared, negative 6t2. And what is its magnitude? Square root of 36t to the 4th plus 36t squared plus 4. Magnitude of r prime, square root of 1 squared plus this thing squared is 4t squared plus this thing squared is 9t to the 4th. Okay, so kappa is magnitude of the cross product over this mess cubed. Okay, plug in 1, 36 plus 36 plus 4 is radical 76. Plug in 1, so I have radical 14 cubed, which is radical 76 over 14 radical 14. That comes out to be 2 radical 19 over 14 radical 14, radical 19 over 7 radical 14. Okay, then let's see. 29, a two-dimensional function. Okay, so that means I use this one. Number 11, page 865. So we still might want to talk about curvature for two-dimensional graphs, right? Function x e to the x. Okay, so I need the first derivative, product rule, first times derivative of the second, x e to the x, plus the second times derivative of the first, x plus 1 e to the x. Do the second derivative, first times derivative of the second, x plus 1 e to the x, plus the second times derivative of the first, which is 1, x plus 2 e to the x. So kappa is the magnitude of the second derivative, which is absolute value of x plus 2. E to the x is always positive, so I can just write it like that. Over 1 plus, okay, it's a little bit tricky, 1 plus this thing squared, x plus 1 to the e to the x squared, all to the 3/2 power. Okay, and you just leave it like that. Okay, then 47, find t, n, and b. R is t squared, 2/3 t cubed, and t. 47. Okay, find the vectors t, n, and b. There's only one problem that's like that. All right, then t has to be 1. It's easy to see from this one. Okay, so first derivative, 2t squared, 1. Magnitude, unit tangent vector is r divided by its magnitude, which is radical. I'm deciding to put this first, 4t to the 4th plus 4t squared plus 1. This very conveniently is 2t squared plus 1 squared, whose square root is 2t squared plus 1. Okay, then I plug in 1. 2/3, 2/3, 1/3. Okay, now a little bit harder to find these derivatives. X is 2t over 2t squared plus 1. So dx dt, quotient root. Bottom times derivative of the top, 2, minus the top times derivative of the bottom, all over the square root of the denominator. Okay, I could clean that up, but I think it's easier to just plug in 1. Plug in 1, I get 3 times 2, which is 6. Plug in 1, I get 8. Divided by 3 squared is 9, so -2/9. For the y component, I do a little trick, except that I messed up over here. 2t squared over 2t squared plus 1, they're almost the same. The trick is to make them the same. I add 1 and quickly subtract 1. It makes it easier. So I'm going to write 2t squared plus 1 minus 1, because I know 2t squared plus 1 over itself is 1. So 2t squared plus 1 minus 1, change that to just 1, because I know its derivative is 0, and write that as -2t squared plus 1 to the -1. Okay. So dy dt is +1, 2t squared plus 1 to -2. Then by the chain root times derivative of the inside, which is 4t. 4t over 2t squared plus 1 squared. Plug in 1, 4/9. And then the z component, this thing, treated as 2t squared plus 1 to the -1. So the derivative is -2t squared plus 1 to -2 times 4t. Comes out to be that. Plug in 1, -4/9. So unit normal vector is -2/9, 4/9, -4/9 divided by its magnitude. Okay, I had the tangent vector. Okay, this comes out to be the square root of 4/81 plus 16/81 plus 16/81, which is square root of 36/81, 6/9. So I'm dividing this by 6/9, which means I'm multiplying by 9/6. So -2/9, 4/9, -4/9 times 9/6. All the 9s drop out. Okay, so I get -1/3, 2/3, -2/3. That's unit normal. And then the binomial is just t cross n. So this is t, this is n. So it's going to be, I component is -4/9 minus 2/9, -6/9. then J is the opposite of -4/9 plus 1/9, double negative, gotta be careful with negatives. K component is 4/9 minus a minus 2/9. Okay, so it's -2/3, 1/3, 2/3 is the binomial vector. All right, so all of that was section 13.3.